Hello everyone, we want to continue on chapter 6, the second law of thermodynamic. Remember we talked about heat pumps and refrigerators. Initially we discussed the heat engines, and we actually talked about the second law of thermodynamic applied to heat engines, and it was the Planck statement. And here we want to talk about the second law of thermodynamic, the classes statement, which applies to refrigerators and heat pumps. So what does it say? It says that it's impossible. So remember that the purpose of the heat engines and refrigerators was the devices were very similar. In the refrigerators, what we wanted to do was to take the heat out of a refrigerated space and basically transferring the heat from a low temperature source to a higher temperature, a low temperature area to a high temperature environment, right? And the purpose of the heat pumps was to transfer the heat from a low temperature environment to a high temperature area. For example, you want to heat up your you want to warm your apartment, right, in a winter season. So anyway, that was what the heat pumps and refrigerators was doing. And what the second law of thermodynamic classes statement is saying is that you cannot transfer the heat from a low temperature area to a high temperature body without having any effect on the environment. With that, we mean that without needing any work input to your system. So if you look at the picture on the right hand side, there is a cold refrigerated space, and then the heat is transferred to a warm environment, and the net work input to the system is 0. This is against the classes statement, which says that you cannot really transfer 100% energy or heat from a cold space to a warm environment by having no effect on the environment. In this case, it's no effect. So this refrigerator violates the classes statement of the second law. Okay, so that's the definition of this. And in fact, the classes statement and the Kelvin-Planck statements are the same. So if you look at these two pictures, first look at the left hand side, we have a heat engine and we have a refrigerator, and the heat engine, and both of them are operating between a high temperature at TH and the low temperature reservoir at TL. So what you see here is the heat engine receiving heat from this high temperature source and produce some work, and it doesn't there is no heat transfer between the heat engine and the sink or the low temperature reservoir. So this violates the Kelvin-Planck statement, right? That was the Kelvin-Planck statement. Now what it does is it transfers that work. So let's assume that it violates the Kelvin-Planck statement. It transferred that work 100%, which is equal to QH, to a refrigerator, and the refrigerator is receiving QL from a low temperature reservoir and transferring QH plus QL to high temperature reservoir, right? All right, so now look at the system. So just consider the whole system. So if you consider the whole system, you see that if you write the net amount of heat transfer in this system that I draw, the combination of refrigerator and the heat, there is a QH right here, QH going back, this QH by that QH will cancel out, and there is a QL from here going to the high temperature reservoir, which results in this picture on the right hand side, right? So that refrigerator is transferring QL to the high temperature reservoir without having any effect on the surrounding, right? So this is in this is against the classes statement of second law of thermodynamics. So if you violate the Kelvin-Planck statement here, you're violating the classes statement as well. So these two statements are really the same, but they apply to different type of devices. So that's it. In next video I will talk about the reversible, irreversible processes and the Carnot cycle.